Hey, good morning, everybody. Listen, I'm going to hand back your exams at the end of class. I'm going to go ahead and hand back the form right now, though. And then afterwards, I'll hand back the actual test after class, or at the end of class. And then you can go over it if you, like you can, I put it online, so you can see which ones you got wrong. So if you hear your name just come on up. Adam, Brianna, Brianna, right? Yes. Jade, Emily, Keelan, Mallory, Madeline. Who's Madeline?
She's coming.
V, Taylor, Michelle. Brianna. Anna.
Thank you.
Emily. Keelan. Mallory. Madeline Arsena. Taylor. Michelle. Bryant, Julie, Cameron, Haley, Claire Chase, Sydney, Eric, Chris, Haley, and Mallory Blanchard. Right?
Okay, I'm sorry.
Yes, Cameron. Where's Brian? Yes. Drew, Megan, let's go. Claire Graham, Virginia Barker, Megan Thibodeau, Skylar, Christina. Brett. Alright, Christina, everybody else. Katie, Kate, Andrew, Bailey, Bryce, Sarah, Megan, Duce, Asia, Amanda, Kaylin, and Ryan. Christina, Kate, Caitlin, Andrew, Bailey, Sarah, Megan, Duce, Kaylin, Maya, yeah, I did earlier. Did I not get theirs? Okay, got it. All right, I'll hand back the rest of it at the end of class. I do just want to go over with you on the website. There's this grade worksheet. If you download that, you can put in the grades for the class. I don't report an average on Moodle because sometimes on Moodle I have things that aren't really part of your average in the way that they should be. Like, for example, your class participation right now is listed as a percentage because I just take, the total number of points that you get. And remember, you get 2 points per correct answer and 1 point per incorrect answer, and no points for no answer at all. And the way that I calculate your grade in the end you can get a total of 50 points. But the way that I calculate that is I ask, well, if they come and they get all the answers wrong, then I want that student to get the full 50 points. And so the way that works out with your percentage is that if you have about 50% right now, then you're on track to get the full 50 points. If you're at 100%, if you're between 50 and 100%, then you're okay. If you're below 50%, and some of you are, then you need to make sure that, one, you're coming to class, and two, that you're getting as many correct as possible. Now, I know we have a bunch of athletes in this class, and I understand. I'll work with you if you have excused absences for athletic things or you're sick or whatever. Then we'll work with you and account for that in some way. But otherwise, just make sure that you come to class. In the end of the semester, almost everybody's going to get that full 50 points because, you are good students. You come to class regularly, you're prepared, and maybe you're not prepared for the questions beforehand, but as we're going through class, just listen to what the answers are. Try to think what the answers are before you answer. So anyway, that's why I don't give you an average on Moodle, because I include things that aren't really part of your average. So here you can see, you can put in your 3 exams. Your project, that's going to be at the end of the semester. It's really a paper. It's a short paper, 1,500 or so words. So then this is your class participation credit. And then these are your top 5 reading quizzes. Okay, we've already had 3. We're going to have a 4th one next week. What's today? Thursday or Tuesday?
Thursday.
It's Thursday. So we'll have another one next week. I don't know when you want to have it. Tuesday? Thursday? The more reading quizzes you have, the better. We'll do Thursday. I'm okay with that. But the more reading quizzes we have, the better, because that means that we'll drop those lowest ones. Already, a handful of you have done really well. Like you have practically all 20s. I think a couple of 20s and then maybe an 18 on the quizzes. And so that's really good. That means that you've had a good, strong start. And by the time you get your 5 quizzes, then you're basically, all your other quizzes are going to be drop quizzes. And that's what I want you to do. I want you to do as well as you can on these first quizzes. I don't like having drop grades because it often encourages students to not work as hard, right? Because, it's late, and he's like, well, I got a quiz tomorrow, and he's like, it'll be my drop quiz. I know that goes to your head, but you don't want to do that. You want to do as well as you can on those quizzes right up front, because you know what? Those quizzes, they count the same as an exam. They do, because there's 5 20-point quizzes. That's 100 points. And so they all add up to be 20% of your grade. Is that right? No, they count more. No, they count the same as the exam. No, they add up to be about 18%. It's rounded off right there. So anyway, on this, what you can do is you can put in your grade. Like let's say that you got an 80% there, and then you can ask, well, what if I just do perfectly elsewhere on my other exams? And let's say I get 100% on my final, on my project, and then I get 50 points on that, and then, these are your reading quizzes. My point is you can play around with sort of what you get on these remaining projects and assignments. There's a lot of opportunity in the class outside of the exams for you to do well. The project, I sort of look at the project as not everybody takes exams very well, although you should be able to do well on my exams. You should be, with reading the book and working through the old tests and going through the notes, you should be able to do well on my exams. But I understand, sometimes you mess up on an exam. So the project is meant to be there as a way, one, for you to pick a topic and go a little bit deeper in that topic from the class, but also, honestly, I put it in so that those of you that do poorly on an exam, that you can use that to pull up your grade, okay? It's not that hard to get a perfect score on the project. If you follow the rubric, and the rubric is clear on what you need to have 3 distinct physics concepts, it needs to be a certain length, it needs to be this and that. If you follow the rubric, 90 to 100% is certain, okay? And then the reading quizzes. You should be able to do well on the reading quizzes. It's not a secret. What do I use for the reading quizzes? Old questions. So you have all the questions at your fingertips. I don't change them. Now the tests, as you saw, I do change those, and those are new and different, but they still cover the same topic, and many of them are pretty much the same. Y'all found that on the test? Yeah. Okay? Yeah. The reading quiz next week is going to be, I don't know yet. You want me to tell you?
You could look at it.
Probably the body section of work. If we're doing it Thursday, it's going to be the body section, which begins on page 92 goes through 102. That's only 10 pages. 92 to 102. That's good. Let's get all 20s on this reading quiz. You're going to say, 20. That's 20. 100%. Okay? 92 to 102. Just 10 pages. Like you could probably memorize 10 pages, word for word, verbatim, right? Huh? Yes, you could do it. People have done that. On what?
Very long. Reading chapter 3 is long.
Oh, but the short section is the quiz.
I appreciate that.
You're welcome. All right. The exam was okay. Like, you know, it was like the average was okay. It wasn't super. I'd love to have, you know, close to an 80% average, and we weren't quite there on this one. But I did have a number of A's, and I'm proud of y'all. I'm proud of all of you for, you know, we want to do good work in this class. It's kind of a fun class, right? I think it's a fun class because all of you are sort of involved with the body in some way, and you get to look at it from a different perspective at how the body functions. And so, in that way, I think it's a fun class, and I hope it is for y'all too. Okay? I will tell you that the students that did well on the exam have done well on other things too. That they've done well on the quizzes and they've done well on the class participation. So everything sort of feeds in together. That if you're doing well on the quizzes, that means that you're reading the chapter and looking at the old test. And then if you're doing well on the class participation, that means that you're listening in class and you're sort of thinking about the material and going along. It's not that they're smarter necessarily, right? It just means that they're being more prepared for those. And so that's what you want to do. Also on the website, there's a how to make an A in this class, where you have advice from previous students. Go back and read those. It's frank advice. I'll tell you what they say. Read the chapter, work through the old test, come to class. That's what they tell you. But read through those, what those students say. Okay? Any questions, y'all? Posted the exam on the website. Take a look at it. If you have any questions about particular questions, then come see me. I'm available to talk to you. Alrighty. So we will do a quiz on Thursday, and it'll be pages 92 through 102. Quiz Thursday, page 92 to 102. All right, so we had started on chapter 3, and the main thing that we've done on chapter 3 so far is defined what is work. And the physics definition of work is a force times a displacement. So in order to have work, if I have a force that's not causing a displacement, no work at all. Or if I have a displacement that's but doesn't have a force attached to it, right? Like I can have that, an object in motion tends to stay in motion, that sort of thing. That I can have displacement without a force. That's also no work being done there. I have to have a force and I have to have a displacement. And then we also talked about the concept of positive and negative work. Now remember, we discussed vectors, and vectors have a direction, and usually signs are used to denote that direction, but work is what type of quantity? Is it a vector or a scalar quantity? Vector or scalar? It's a scalar quantity. That means it doesn't have a direction. Okay, it's only a magnitude, like time, mass, charge, those are all scalar quantities. The work does not have a direction. However, what the positive negative means for in work is that if you're doing positive work, you're giving energy to something. I'm saying here, take this energy, you're speeding it up, or you're changing its potential energy, or you're changing its thermal energy. If I do negative work on an object, that means that I'm taking energy away from that object. Okay? And the example we give, force that often does negative work, is the frictional force. The frictional force does negative work, and that means that it slows down the object. Okay? It takes energy away from that object. We also talked about how the force has to be in the same direction as the displacement. Or rather, it has to be parallel or anti-parallel, either in the same direction or opposite direction, but not like this. Because if I have a force that's cockeyed to the displacement, only a component of that force is actually doing work. We sort of seen that before, right? Remember we were talking about the door? We saw this with forks. Where only a component of the force was doing a torque. It's similar to work, that only a component, the parallel component or the anti-parallel, same direction, opposite directions, that those are the components of the force that are doing work. Work is kind of important because we'll talk about energy later. And work is the foundation of energy as we move into the body and how the body uses energy.
What's an example of perpendicular force?
A perpendicular force. So, for example, I have a perpendicular force acting on me. I have two perpendicular forces, right? Y'all know what the two perpendicular forces are that are acting on my body? Perpendicular to the floor, right? The normal force is one. That's what normal means, right? Perpendicular. And then what's the other? The weight, right. So I have the normal force going up, the weight going down, but if I have a displacement in this direction, those forces are not doing any work because I'm not moving up and down. Now if I do like this, then those forces are doing work because I have a force acting in the vertical direction and I have a displacement. If I jump up, what is the sign of the work that's being done by the gravitational force as I move from the floor up to the topmost part of my trajectory? What do y'all think? Let me repeat the question. So if I jump up, I'm moving up out of the gravitational force. What is the sign of the work as I move from the bottom to top? It's negative because my force is down, but my displacement is up. And when those things are opposite one another, that's negative work. Because what am I doing if I'm going up? I'm speeding up or slowing down? I'm slowing down. That's right, I slow down as I go up because that gravitational force is pulling me down, right? Pulling me down and slowing me until I get to the top. Now when I get to the top and turn around and come back down again, what is the sign of the work then? Positive. Because the gravitational force is down and my displacement is down. Okay? You good? That's sort of what we did last time, talking about work and energy. Now, energy, we have lots of different kinds of energy. I think they give about a half dozen or so that you'll need to be familiar with. And the first is kinetic energy, and that's the energy of motion. Kinetic energy is given by this. It's given by 1/2 mv squared. That's an equation you need to know, but it's on your equation sheet. But you do need to know how kinetic energy is related to mass and speed. So m here is the mass. You know, we measure that in kilograms. V is the speed. And we measure that in meters per second. Now, we've already said this, but let me formalize it, because this is called the work energy theorem. And the work energy theorem says that if you do work on an object, then the energy changes. That's all it says, just that the work is equal to some change in energy. You work on an object, then the energy changes. Now, usually, this can be any kind of energy, and we'll talk about some others: potential energy, kinetic energy, chemical energy, thermal energy. But usually, when we talk about the work energy theorem, we talk about it in terms of kinetic energy. That if I do work on an object, I change its kinetic energy. So if I push this over a displacement, I change its velocity. I increase its kinetic energy. So if I do work on an object, I will increase, or if I do negative work, I'll decrease the kinetic energy of that object. So for example, if you catch a ball, right, then you're taking it from being a high speed to a low speed, I'm doing negative work because I'm applying a force in that direction, even though the ball is going in this direction. Negative work, opposite force and displacement, and I'm taking away the kinetic energy of that object. All right? You with me? All right. So let's try these questions here. You push a car at constant speed. What is the work done? Let me get this up. And yeah, you got to be careful with work questions because when we're talking about work, there's the work that's done by a particular force. Like I can ask, what is the work done by the gravitational force? And then there's also just the total work that's being done. And the total work that's being done is what causes the change in energy of the object. Y'all follow me? So the total work here, whatever our total work is equal to our change in kinetic energy. Then I might have multiple forces that are acting on an object, and some of them might be doing negative work, and some of them might be doing positive work. But it's the total work that we're really thinking about when we think about the change in energy of the object. Let's see how you do on this, and I'll explain more. Okay, I need to explain more. I don't get that. If I do, let's say I have two forces that are acting on an object. Okay? She's pushing in that direction, and I'm pushing in this direction. Okay? Our net force is 0, right? And if the net force is 0, that means that the work is 0. But in addition, do you mind standing there? Don't make me look wimpy, so don't push too hard. You might make me going back the other direction. We're going to go in that direction. No, we can forget this direction. So push in this direction. Now, we're moving at a constant speed, right? At about, I don't know, a meter every 2 seconds. Okay, you can say that. So if we're moving at a constant speed, that means the acceleration is what? If I'm moving at a constant speed, what's my acceleration? 0. It's not accelerating. That means that my net force is what? 0. Now, Jillian was pushing with a force, but then I was pushing with an equal but opposite force. And the result was that this thing was moving at a constant speed. Was she doing positive or negative work? She was doing positive work because it was moving in this direction and her force was in this direction. Was I doing positive or negative work? Negative work, because they are opposite one another. So what was the sum of our works? 0. Right. So if I push a car at a constant speed, some of the forces are doing positive work, some of the forces are doing negative work. For the car, what's the negative work? Frictional forces, right. You ever push a car? You ever get out and push a car?
Yes.
Yeah. When I was a kid, it seemed like our cars were either breaking down or running out of gas all the time. Who's ever run out of gas? See, my wife, she never ran out of gas because she was pretty wealthy. I mean, she was middle class. But we used to run out of gas like all the time. And we'd go to the store and we'd get like $2 worth of gas, which is, you know, several gallons. And we'd get like $2 worth of gas and then we'd go. And then we'd run out of gas. And we'd be like, why did we run out of gas? So we had $2 worth of gas in our car. Anyway, if you're pushing a car at a constant speed, the work is equal to what? 0. Right. A lot of you have A, of course, right? Because you're thinking I'm pushing. That means I'm doing positive work. But that's not what this question asks. It's not what is the work done by you or what is the work done by friction. It is what is the work done on the car. So the answer here is A. Everybody got that? No, not all of you have A. The answer is A. I mean B.
Yeah.
B, yes, I'm sorry. B. B, B, B. All right, I'm going to stop it here. Okay? So here, what's implied here is what is the total work done. And the work done by you is positive. The work done by friction is negative, but the sum of these two is going to be 0. When I add up a positive and negative work, if they're equal in magnitude, then they'll go to 0. Which of these is a unit of work? Just, how do you calculate work? And then, the units for those individual variables. So what is the unit for work? All right, we'll stop at 50. Okay, which of these is a unit? Well, listen, work is force times displacement. Whenever you have one of these questions, just write down the formula that you know to calculate that. And I know the force is newtons and D is meters. I like to give those kinds of questions sometimes. I think you had one on your exam, and I think it was what are the units of force? And so you'd start with that, and you'd say F equals ma, and you'd say, well, I know mass is kilograms, and I know A is meters per second squared. That's how you'd get that. The units of work are also going to be, we'll see a little bit later, the units of work are also going to be in joules. You might have heard joules before, right? You sometimes hear it when you're talking about food items because it's a measure of energy. It's similar to calories. It's a measure of energy. So the units of work and energy are the same. And we'll see these later. Let's just go ahead and give them Newton meters, joules, little calories, big calories. I think that's all that we'll see actually. Yeah, that's all that we'll see. Okay? So we have a number of different types of energy, and your book has sections or chapters on each, or paragraphs on each of these, the different types of energy. You need to be familiar with what they are, where you find them, and when they're relevant. The first is potential energy. Potential energy, which is U, that's our abbreviation for it, is stored energy or work. That's you. Potential energy is the potential for motion. An object with potential for motion has potential energy. And then let me just remind you what the variables are. I think that sometimes we just get confused. All these letters start swimming around in your head. But just off here to the side, remember that our work is given by W. Our kinetic energy is given by K. Those are easy, I think, because they just, they're the first letter. But U is our potential energy. Many different types of potential energy. Elastic is one. Like a rubber band. If I stretch a rubber band and I let it go, do I have one up here? I don't, I'm sorry. If I stretch a rubber band and I let it go, it has the potential for motion, right? Or if I have a spring and I compress it and I let it go, then it has the potential for motion. So elastic is one. Gravitational. Gravitational energy, if I have something and I hold it at a certain height from the floor, from the earth, it has the potential for motion. If I let it go, then it moves. The gravitational energy. Chemical, and we'll deal with a lot with chemical energy later. Because, food is chemical energy. It's how we get energy in our body. Then there are some others too. Nuclear, we'll deal with that at the very last chapter that we have in this class. And electric potential, we'll see that as well. Electric potential energy. Nuclear energy is just the energy that's bound up in the nucleus. And electric potential energy is the energy that's bound up between two charges. So if I have two charges right here, and I hold them in place, say I have a positive charge and a positive charge, if I let those things go, what are they going to do? A positive and a positive? They're going to repel one another. Like charges repel, opposites attract. High school physical science, probably. They're going to fly apart, and they have the potential for motion. We'll have a whole chapter on electric potential and current and voltage and the nervous system. It's kind of a cool chapter. Nuclear energy is similar because you know that in the force between two charges, if you bring charges really close together, the force gets really, really big. And so it's kind of a mystery, and it was a mystery for many years, as to how you can have the nucleus of an atom, which is just protons and neutrons, right? Positive charges and neutral charges, neutrons, that are all bound up really, really, really close together, like why they don't just fly apart. Because they should, right? Positive charges should all just fly apart. But they have particular type of forces, other type of forces that bind them together. And we'll talk about that, the strong and the weak nuclear force. That are immense forces, much greater than any electric or gravitational force. Okay? We'll see that in the last chapter. We'll talk about it. All right. So let's say that you move an object of mass m to height h. So I have an object of mass m, and I move it through a distance h. I just want to know what work has been done. I have a force that I have to apply over a certain distance, h. What work do I do moving that mass m through height h? Is it m times g divided by h, f divided by h, m times g times h, or m divided by g times h? How do you find work, first of all? What's our definition for work? Force times displacement. That's where you're starting at. And then if I do the force times displacement for this object, what expression does that give me? What is my displacement in this case? What's the magnitude of my displacement? The height, right. I'm moving it through a displacement, h. And I want to do the force times the displacement. Is this one a force times a displacement? No, this is force over displacement. Rethink your answer, B. If you put B. All right. Let's stop at 125. 125. Okay, good. C is what we're getting at. That the force that I have to apply, it has to be at least equal to the weight in order to move it up. And then the distance is going to be equal to h. So I can put those together, and I get work is equal to force times displacement. That's equal to m times g, that's F, times h. And so this is our expression for gravitational potential energy. If I pick up an object, I apply a force to it that causes it to move to a certain height, then this object now has potential energy that's equivalent to the mass times the acceleration due to gravity, which of course is what value? G is what? What's the value for G? There, what is it?
10 times.
Right, 10 meters per second squared. Right, so m times g times h That is our gravitational potential energy. So U is equal to m times g times h. And particularly, this is gravitational potential energy. And remember that G from the previous, I don't know, 1 or 2 chapters ago, is 10 meters per second squared. It's just equal to the weight, that's the force you have to apply, times h. Now, your book talks about this, how h refers to the distance from some reference point. I think your book goes into this. I'm not sure. I mean, the reference point. I don't really worry too much about the reference point. When people talk about gravitational potential energy, they don't usually talk about an absolute value of potential energy. Instead, they talk about a change in potential energy. If I have an object right there, and I give it some force, then I talk about the change in potential energy from there to there. And your book sort of uses that idea, that my potential energy has changed. But the potential energy has also changed from here all the way down to the floor. It depends on your reference point. In one case, I have a reference point here. And in that case, the potential energy, or the change in potential energy, is different from if I use the reference point on the floor. Which is larger, using a reference point on the floor or using a reference point on the desk? The floor, because my h value is bigger. I talk about a different height here than here. I find it useful in this class just to talk about h at the floor. So we'll always let our reference point be the earth. But h does refer to the distance from some reference point from to the height. But we'll always let the reference point be the ground. When you drop the object, the potential energy is converted to kinetic energy. All right, let's try a couple of questions here. By what factor does the kinetic energy of a car change when its speed is tripled? And just to remind you, this is on your equation sheet. This is relevant for both of these questions. Is equal to 1/2 mv squared. That's my kinetic energy. So what happens when I triple the speed? Remember what happens when I have a quadratic relationship. I'm looking at the relationship between k and v. What happens when I have that quadratic relationship as opposed to a linear relationship where, like, for example, k and m have a linear relationship, k and v squared have a quadratic relationship. We should use those words to describe our own relationships with people. All right, let's stop at 1:30. 1:30. All right, good. Okay, good. C is right. It's going to be 9 because I have 1/2 mv squared equals k. If I triple v, that means 3 squared. I have a factor of 9. You had one or more questions like that on the test. If you missed those, when you get it back, take a look at it. If you missed those, you might want to come see me. I can help you with those because you'll see those types of questions again as we move along, okay? All right, a car starts from rest and accelerates to 30 miles per hour. Which takes more energy? To go from 0 to 30 miles an hour or 30 to 60 miles an hour? Just 60 for mistake, I don't know why it's saying. All right. I don't think this is in the book.
I really like the concept. Unless it's
Okay.
Hmm.
All right. Let's stop at 50. 50. Look, my dad, we were kind of poor growing up, right? Like we run out of gas and all that. My dad was like the slowest driver ever. He would go to work in the morning. He left really early, like at 5 o'clock, and he had about an hour to get to work. But he would drive to work at about 35 miles an hour. And he'd have a line of people behind him. 5, 6, 7, 8 cars, even at, 4 or 5 o'clock in the morning. And so every so often he'd just pull off the side of the road and wait for people to all pass him. He even knew who they were, and then he'd start driving again. Why do you think he drove so slowly? It burns less gas to drive more slowly. When you drive faster, it uses more gas. And for a very simple reason, that when you drive faster, it requires more energy. So if I were to plot the kinetic energy versus the velocity, if I make a plot of K versus V, what it's going to look like is this. Right? Because it's a quadratic relationship, right? You know what that is.
I don't. We don't.
It's a parabola, right?
That's great. That's just a graph.
It's a graph from algebra. But the graph looks like this, because you think about it, if I double V, if I go from here to here, then the kinetic energy quadruples. So if I have a small change in V right here, I get a big change in K, because it's a quadratic relationship. And so if I go from, say, 0 to 30, I just have a tiny little bit of energy that I use. There's a tiny change in energy. But notice if I go from 30 to 60, I get a much bigger change in energy. So the answer, which most of you did not get, is B, 30 to 60. Mallory, did you get that right?
Okay, so I don't know where I read it, but it was like, once something's already in motion, it takes action.
Okay, yeah, so she said, somewhere it said that once something is already in motion, it takes less energy to keep it in motion. Is that true? Where did you read that? I'd have to read the context. It depends. Like, it depends on what the opposing force is. Yeah. But it is definitely true that the faster you go, it requires more and more energy to go those faster speeds. No, it's not because of frictional forces. It's not because of thermal energy that's lost. It's just simply because of the relationship between K and V. That there's a quadratic relationship between K and V. I can show you where it comes from, but it's calculus to get to that. But between K and V, you have that quadratic relationship. So higher and higher speeds, more and more energy. So next time you're with a buddy or friend, and they're driving really fast, tell them, hey, did you know about the quadratic relationship between kinetic energy and velocity? And they'll say, no, I didn't know that. It's like, the faster you drive, the more fuel you're going to burn. And see what they say. Okay? All right. Other types of energy. Yeah, your book talks about mechanical energy. Mechanical energy is really just the sum of potential and kinetic. So E then is equal to the total amount of potential energy plus the total amount of kinetic energy. So for example, where's my little flash drive? I'll use this.
E is just energy?
E is just energy. It's the mechanical energy, though. It's referring to the mechanical energy. So if I throw this up, at various points in the trajectory, it's moving, And it also has gravitational potential energy. So as I throw it up, like right here, halfway, it's moving upwards, and it's at a distance from the ground, so it has both kinetic and potential energy. What about up here at the very top? What type of energy does it have?
Potential.
Does it have kinetic energy? Is it moving at the top of the trajectory? At the very top? Right up here? No, it's not moving. Right? If you watch it, it goes up, it stops, and then it comes back down again. So there's this trade-off between kinetic and potential energy. As it goes up, it gains potential energy, but then it loses kinetic energy. And then as it comes down, it gains kinetic energy, but it loses potential energy. Let me draw a little picture. So if I have a ball that goes up, and then it comes back down again, at the top, I have V equals 0, and that means that K equals 0. As it's going up, it loses U, and it gains, or excuse me, I'm sorry, that's opposite. It loses K, and it gains U. Loses kinetic energy, it's slowing down, and it gains potential energy, it's gaining height. It's getting farther and farther away from the Earth, so it gets more potential energy. And then as it's coming down, it gains kinetic energy. It gains K. It's speeding up, right? And it loses potential energy. This considers our total mechanical energy, considers energy from position, that's U, and from motion, that's K. If I want to think about it in terms of the variables, this is H and this is V. It's related to the height, the distance from the surface of the Earth, and then also the velocity of the object, or the speed. There's a law, the law of the conservation of energy, or conservation of mechanical energy. And it says that energy transforms from U to K or vice versa. But the total energy remains constant. So if I think about this ball moving up and down through this trajectory, it goes up, it comes down, it has a certain amount of energy. And here at the beginning, let's see, I'm going to draw it like a bar graph. The total amount of energy is right there. That's E. Right down here, it has nothing but kinetic energy. It has all kinetic energy. So that's K. And the potential energy is basically 0. So that's U. But up at the top, the total energy is still the same. That's E. Now my kinetic energy is 0 because it comes to a stop up there. And my potential energy is now at its maximum. It's the same as U. So as my object goes up, the kinetic and the potential energy, they trade off. But the sum of the kinetic and potential energy will always remain the same. So the total amount of energy will always be the same unless you have some work that's being done on the object. If you have work that's being done on an object, then it changes the amount of energy. Work is equal to delta E. Okay? Yep. All right. So think about the roller coaster. I have a roller coaster, which my wife, by the way, loves roller coasters. Let me tell you a parenting story. Probably not a good idea to model this, but it worked for us to get what we wanted. We went to Six Flags in St. Louis a few years ago. I think my son, he was 10, and my daughter was 7. And my wife loves roller coasters. Maybe, roller coasters, whatever. But she loves roller coasters. So we went to Six Flags, and they had some pretty decent roller coasters there. And they had a wooden one that she really wanted to ride. I think it was like Lightning or something, Thunder and Lightning or whatever. I don't remember. But anyway, we were waiting to get into Six Flags. We were there when it opened, and it opened up, and we lickety-split went to the back of the park where the roller coaster was and jumped on. And we've been sort of talking it up with our kids all along because they'd never been on a roller coaster. And we got them all excited. And so we just sort of took that excitement and just ran with it, like literally ran with it to the back of the park. We were the only people on the roller coaster. We jumped on. There was no waiting in line. We jumped on, and then about the first 5 feet, my son, no, I want up. I don't want to do this. But we did get to ride the roller coaster, even though he really hated it. And my daughter, she didn't really like it either. But then later in the day, we wanted to ride more roller coasters. And so we started telling them that we're going to go ride the train. We're going to ride the train. But they're not stupid, right? Are they stupid? So they knew that the train was really a roller coaster. But they did go on it after all, and it was fine. So don't trick your children if you have children, or if you have them in the future, don't trick them. All right? So think about this roller coaster. I have a car at the top, and it sort of goes off the top of this and goes through the different heights to B, C, and D. And I want to know, where is the kinetic energy greatest? Where is U greatest? And then where are they equal? So the first question, which we'll do as a clicker, is where is the kinetic energy greatest? Is it at A, B, C, or D? And notice they're all different heights. So where is the kinetic energy greatest for this? Okay, doing pretty well. You can ask your neighbors what they put. About half of you right now don't have the correct answer. But ask your neighbor. Remember, the kinetic energy is going to be greatest where you have the highest what? Highest what? For kinetic energy. The kinetic energy is related to what? To speed. That's what you said, Sarah? Yes. To speed. So the kinetic energy is greatest where I have the greatest speed. Where is the kinetic energy greatest? All right, let's stop at 110. 110. B is right. Let's try the next one, then I'll explain. Where is U greatest? So for this one, it was B. Where is the potential energy greatest? All right, let's stop at, what, 38? 38? Okay, good. A is right. My potential energy is greatest at A. And let's answer this last one, then I'll give you a joke. All right, where are U and K equal to one another? Where are the potential and the kinetic energy equal? Remember, they trade off from one another. They always add up to equal the same amount, but they trade off. And so where on this roller coaster are the potential and kinetic energies equal to one another? All right, pretty well. I'm going to stop at 40. 40, just 5 more seconds. Sorry, it's thinking. You scared the clicker software or something. Wow. Many of you got the right answer. I'll show it in just a second. But the answer is C. All right? Because at C, we're at roughly h over 2. And so that means at point C, we have half the potential energy that we had originally, and then we also have half of the maximum kinetic energy, that you split it in between those two. Okay? What did the blanket say when it fell off the bed? What did the blanket say when it fell off the bed? You say, I don't know. Oh, sheets. All right, let's see here.
Yeah, where you get off? I feel like you send you off before class. Look up what you were doing today.
Ugh. Give me just a second. This is still thinking. I'll show you this while we're thinking. So this is a roller coaster of sorts, right? And so in this, I have a start, a little metal ball here. And so up here, it has lots of potential energy, right? Because it's not moving, but it's a height from the ground, so it has potential energy. And then as I move through, I change from potential down to here where it's going the fastest that it can. Right here, it has a little less than half the original kinetic energy that it had. So it slows down. And then down here, it has what type of energy only? What type of energy does it have? No. What's other than potential? Kinetic, right. So it's going the fastest at this point, so that means that it only has kinetic energy. Okay? Make sure that you'll probably have a question that's something similar to this roller coaster. I'm not going to ask you to calculate the potential energy or the kinetic energy, but I do want you to know what happens to the different types of energy as this object moves through these different heights. That when it's at a big height, it has all potential energy, the maximum, and then when it's at a lower height, at the lowest height, it has all kinetic energy. It's lost all of its potential energy, and that's gone into kinetic energy. And then when it's somewhere in between, it has a mixture of potential and kinetic energy. All right. Electrical energy, just sort of listing a few different types of energy. We'll have a whole chapter on electrical energy. It's the energy of charges. It's kind of a cool chapter because the nervous system is a very interesting system in your body. Did y'all study the nervous system? The cells are remarkable, the way that they transfer information in the body, and they operate at lightning fast speeds. So it's quite remarkable how the nervous system works, and we'll talk about the basics of the electricity involved in that. The energy of charges, energy is greatest when charges are closer because the forces are greater. So if I have two positive charges, they feel forces that are opposed. Like charges repel. Remember that from high school probably? But if I bring them closer together, if I have two positive charges that are really close together, the forces that act on those charges are much bigger. Because we'll see in a later chapter that the force is inversely proportional to the distance of separation. The closer you bring those things together, the bigger the force. It's similar with magnets, right? You've ever tried to push two magnets together, the positive ends of two magnets? The closer you get them together, the harder they push apart. It's a similar thing with magnets. Okay, internal energy is potential and kinetic energy of molecules and atoms. If you have a material, a gas, or even a solid substance, the atoms inside of that are moving around. Right? They all have a certain velocity as they move around. And the velocity of those molecules and atoms is going to determine how much energy that substance has. Do y'all know what type of energy we call that? That's governed by the velocity of the atoms and molecules within them? Well, you know, it's called thermal energy. And so when you take the temperature of something, it's a measure of how quickly are the atoms or molecules moving around. You ever think about it that way? In fact, there's a whole field of physics called thermal physics or thermodynamics, where you really just start with K equals 1/2 mv squared, and you ask, okay, well, if this particle has this amount of energy, then how does that affect the temperature of the substance? And the more that it moves around, then the more that it's going to, the higher the temperature. So this is similar to thermal energy, although we'll talk about it in a little bit different way. Thermal energy and the temperature of this substance is governed by how fast they're moving around. Let me write that out actually. The temperature is determined by the speed of the molecules or atoms. We'll talk about that. We'll also talk about heat. And heat is a lot like thermal energy, except when we talk about heat, it's the transfer of thermal energy. So when we talk about thermal energy, we just take a snapshot of that substance. And we say, okay, this object, has so much energy that's due to the motion of the particles within it, and we call that thermal energy. But we also talk about the transfer of energy, and that's heat. You've done calorimetry before? Q equals mc delta T? Yes, you did. Calorimetry? We'll see that. If you haven't, that's not a big deal. But we'll see calorimetry a little bit later in this chapter. So we have several of these chapters coming up. So when heat is added, the temperature increases, or it changes phase. And we'll talk about phases in a later chapter, but you know, solids, liquids, gases. And then chemical energy is just stored energy in molecules and atoms. We'll see chemical energy. We're not really going to deal with the reactions that occur, but we'll see chemical energy later in this chapter as we talk about metabolism. But if you ever take, I think Chem 208, any of y'all take Chem 208? Or Chem 109? Y'all take 109? You already took it? Okay. Did y'all deal with that? The energy wrapped up in chemical reactions. Y'all do that, right? Yeah. And particularly in dietetics, they do that, the chemistry for dietetics. Because you want to know, if you have these different foods, then how are the energies released when you process them in your body? Electromagnetic energy, light and radiation, we'll have a chapter on that. Acoustic energy, sound, nuclear energy, we'll have chapters on all these. Okay? All right. Let's just define these systems, and I'll give you a test back. Energy is conserved in a closed system. And so an open versus closed system, your book defines these, but let me try to define them just in a few words. In an open system, energy or work can be transferred into the system or out of the system. So if you think about it like as a box, it's open, and I can put energy into the box. I can add energy into the box. That usually means that there's some external force acting on the system, right? A closed system means that no energy or work enters or leaves the system. So in a closed system, you have a box, but it's closed up. And so if you try to put any energy into it, that energy is just bounced away. Like you can't put energy into a closed system. And the book talks about how your open and closed system, it really just sort of depends how you define the system. Because like if you have, say, a guy on a bicycle that's riding along the road, if you just look at the bicycle, then you would consider that to be an open system. Because you're putting energy into the bicycle, the guy is pedaling, and that's putting energy into the bicycle and causing it to change energy. So that would be an open system, something that you can put energy into. But if you expand your view of the system to include the guy and the bicycle, then that's basically a closed system. Because you're not putting any energy into it unless the guy is eating or whatever while he's riding the bicycle. That he's putting energy into the bike, but he's part of the system. So that would be a closed system. And then if you expand it farther and farther and farther until you just look at the entire universe, then the universe we think of as a closed system, that we don't think of any energy coming into or leaving the universe. So the closed and open system thing it sort of depends on how you look at it, that if you look at a particular part of a system that's taking in energy from somewhere, that would be open. But if I expand it to include whatever's putting energy into that thing, then that becomes a closed system. And your book talks about it in greater detail. You should certainly before the quiz read through that section. Okay? Let me hand back your test, and I'm going to pull up the old quizzes. It's on this site. So if you just go to Spring 2019, it's here. Or you can pull it up on your phone too if you just want to check the ones that you got wrong. Did anybody not get your, who we got? Taylor and Madeline? Madeline, what's your last name? Arson. Taylor. All right, so come and get your test, and then y'all can go. But I'll be around if you have questions. Oh, sorry. I'll be around if you have questions about any of the questions. That's why I'm letting you out early. So all right, Adam, Anna, Brianna, Jade, Emily, Keelan, Mallory, Marino, Madeline, Arsenault, B, Jillian, Taylor, Rochelle, Brianna, Kate, I believe, Emily, Keelan, Mallory, Madeline, Arsenault, B, Jillian, Taylor, Michelle, Bryant, Julie, Cameron, Haley, Claire, Chase, Sydney LaFern, Ari, Chris DeFrancis, Kaylee Claymore, Mallory Blanchard, Rue, Megan Lesko, Claire Graff, Kenya Barker, Megan Thibodeau. Michelle? Brian? Let me see this is. Did I say somebody? Starts with a K? You want to start with a K? Oh yeah, I'm sorry. Hard to read this. Haley? Chase? Aaron? Chris? Haley? Langford? Trip? Kenya? Megan Thibodeau? Skylar? Christina? Katie? Caitlin Bomalong? Andrew? Bailey Hughes? Bryce Button? Christina? Caitlin? What one? Sarah Ramirez, Megan Duce, Deja, Amanda Hedrick, Victor? Kaylin, Julia, Jemiah. Alright, I'll be around for a bit, so if you want to go, that's fine too. And I'll be around if you have any questions about what we're doing. Let me know when you're ready, I can move it down. Or you can look up on your phone. Huh? Yeah.